All right, so far, in order to find the area under the curve, we've looked at the slice part, and then we've looked at the approximation part. Now we want to look at the refine part. So we spent a good bit of time getting formulas for right endpoint approximations, left endpoint approximations, and midpoint approximations using n rectangles. So remember, that was the point of all this, was to use rectangles to approximate areas under curves. So now we want to do the refined part. Now we want to let the number of rectangles go to infinity. And in order to do that by hand for some very easy examples, because this is actually a hard problem, we'll need a few of these formulas. So the sum of the first n integers is just n times n plus 1 over 2. So for example, right, the sum of the first 5 integers, if I start at 1 and stop at 5, of I, that's 1 plus 2 plus 3 plus 4 plus 5. Well, if you add all that up, you do get 15. And if you let n equals 5, then 5 times 5 plus 1 over 2, that's going to be 30 over 2, which is also equal to 15. So we're basically just trying to get formulas for each one of these things. So here's a formula for the first I squares, the first n squares. So that's n times n plus 1 times 2n plus 1 over 6. And then here's a formula for the first n cubes. So that's n times n plus 1 over 2, all squared. You can find formulas for the general, right, the sum of the first n fourth powers, the sum of the first n fifth powers, so on and so forth. But just to get a basic idea, let's just concentrate on these first 3 in order to find the exact value, right, the exact value for the area under the curve. Okay, let's look at an old example, the function x plus 1 on the interval from 0 to 2. We looked at some approximations using 6 rectangles. We computed the actual area. We saw that that was equal to 4. Now let's see that this slice, approximate, refine method actually gives us the answer 4 that we know we should get. So I'm going to use the right endpoint approximation using n rectangles to find the area under x plus 1 on the interval from 0 to 2. So step number 1, find delta x, right? Using this uniform partition, I know that delta x is b minus a over n, so I get 2 minus 0 over n, so that's just 2 over n. So here's my delta x. We know what the right endpoint approximation using n rectangles is. It's delta x times the sum starting at 1, stopping at n, of f of a plus I delta x. Remember, this thing was the height of each individual rectangle. So this is the height of the ith rectangle. So now a in this problem is 0, and delta x in this problem is 2 over n. So I really just get f of 2 over n times I, right? 0 plus 2 over n times I. So really r sub n is this thing, 2 over n, the sum, I goes from 1 up to n, f of 2 times I over n. But what's f? It's really x plus 1. So everywhere I see an x, I'm going to write 2I over n. So now instead of writing f of 2I over n, now I've got 2I over n plus 1, right? Just like the function. So I need to work this thing out. What is this thing in simpler terms? If we can get this thing written without an I in it, that's the goal, right? So I know that sums go through constant multiples and sums, right? So 2 over n is a constant, right? It doesn't have an I in it, so that's a constant, so I can factor it out. So I can write the 2 over n on the outside, and I get 4 over n squared. And then I can break this sum up, right? So it's the sum of 2I over n plus the sum of 1. And so now here I just get 2 over n times the sum of 1. So basically I just moved this sum through this sum and this constant multiple. Make sure you're good on how I got from here to here. That's just using that linearity, right? So that's linearity of the sum. That was that theorem we saw a few videos back that says the sigma notation goes through sums and differences, and it also goes through constant multiples. Okay, so now I've got 4 over n squared, the sum of the first n integers, and I've got a formula for that. And then I've got 2 over n times the sum, right, adding 1 to itself n times. I've also got a formula for that. So we saw in the last slide that the sum I equals 1 up to n of I, that's just n times n plus 1 over 2. And then when I add 1 to itself n times, that's just going to be n. So this thing now doesn't have any i's in it, so that's good. So now what I can do is I can switch the 2 and the n squared, and so 4 over 2 is 2, and then n plus 1, n times n plus 1 over n squared is just, it is what it is. And here I'm just going to get a 2. So 2 over n times n is just 2. So here is a good final answer for r sub n, right? This thing, this expression only depends on n. We have gotten rid of all of the i's. That's the goal. Get rid of all the i's. So now to find the exact answer, I just need to let the limit as n goes to infinity, right? N is the number of rectangles. So the exact answer, right, the area is the limit as n goes to infinity of r sub n. And what's that going to be? Well, this fraction with n's in it, right, it's a degree 2 over a degree 2. So n squared plus n over n squared. So the limit as n goes to infinity, we just look at the ratio of the leading coefficients. So that's just going to be a 1. So this is 2 times 1 plus 2, which is equal to 4. And that's what we expected to get, right? So again, this would be a good final answer for finding the exact area under the curve x plus 1 on the interval from 0 to 2. All right, let's look at the same example again using the left endpoint approximation. At the end of the day, we should get the same thing, right? The left endpoint approximation is approximating the same thing as the right endpoint approximation. So after n goes to infinity, we should expect to get the same thing. So again, the function is x plus 1. We're on the interval from 0 to 2. Now we want to use L sub n. Again, delta x is the same thing every time. It's 2 minus 0 over n. That's the number of rectangles. So here, again, I'm just going to get 2 over n. So the left endpoint approximation is given by this thing. That's the formula, right? Delta x is 2 over n. A in this problem is 0. And then I times delta x is just 2i over n. So 0 plus 2i over n. So that's just f of 2i over n. So now what's f? Well, it's x plus 1. So I just replace x with 2i over n. And so I get 2i over n plus 1. So now, sums are, or the sigma notation is linear. So it goes through constant multiples and sums. So I can factor the 2 over n out. And here I get 4 over n squared. And then in the second sum, I just get 2 over n times the sum of 1. So that's how I got from here to here. Again, that's just that linearity of the sigma notation. That's a theorem from a couple videos back. Okay, so now remember the goal is to write this thing down without any i's in it. So I've got a formula for I equals 0 up to n minus 1. So the sum of the first n minus 1 integers, the sum of the first n integers was n times n plus 1 over 2. So the sum of the first n minus 1 integers, it's n minus 1 times n minus 1 plus 1 over 2. In other words, the sum of the first n minus 1 integers is n minus 1 times n over 2. So in the second sum, I'm adding 1 to itself, starting at 0 and stopping at n minus 1. So how many times did I count 1 Well, if I start at 0 and stop at n minus 1, that means I add 1 to itself n times, right? So here I get 2 over n times n. And so now, just to get all the fractions together, here the n's will cancel and I'll get a 2. Here I can switch the n squared and the 2, and I get 2 times n minus 1 times n over n squared. And so now all we have to do is let n go to infinity, right? So the actual area, it's the limit as n goes to infinity of this expression we got for Ln, right? So this thing, as n goes to infinity, this fraction will go to 1, right? That's a degree 2 polynomial over a degree 2 polynomial, and the leading coefficients, that's just 1 over a 1. So I get 2 times 1 plus 2, so again, we get 4, and that's what we expected to get, right? Here's the last example that we'll look at. So we want to approximate, or actually we want to find the exact area of the function y equals x squared on the interval from 1 to 2. So we want this, we want the area of the region under the parabola and then on the interval from 1 to 2. So step number 1, same as always, find delta x. So that's 2 minus 1 over n. So if we're going to use n rectangles to start, then we know the width of each rectangle is 1 over n. And now let's use the right endpoint approximation. You could use the left endpoint approximation or the midpoint approximation. I will typically just use the right endpoint approximation. So here we know that's delta x. The sum I goes from 1 up to n, the number of rectangles, f of a plus I delta x. So in this case, a plus I delta x is going to be 1, right? That's a plus I times 1 over n. So we've got 1 plus I over n, and then we want to take that thing and plug it into the function x squared. So I want to take 1 plus I over n and square it. So again, delta x, 1 over n. So we just need to work this thing out. Okay, so let me go ahead and FOIL this thing. So here I get 1 over n, the sum, right? And now it's going to be 1 plus 2i over n plus I squared over n squared. Just FOIL this out, right? You know, a plus b quantity squared is a squared plus 2ab plus b squared. So that's how I got from here to here. And now I know that the sigma notation is linear. In other words, it goes through sums. So instead of writing a single sum, I can write 3 different sums. And I also know that sums go through constant multiples. 2 over n is a constant with respect to this sum. The moving part is I. And that's the thing we want to get rid of. So the sum of 2i over n just becomes 2 over n times the sum of I. And the same thing here. Right, now I get the sum of I squared, and I'll write the 1 over n squared out in front. So make sure you're good on how I got from here to here. That's just using the fact that the sum is linear. Okay, now, what is each of these things? So in the first sum, I'm adding 1 to itself n times, so I get just n. So this thing is just n. So 1 over n times n is the first summand here. Next thing is 2 over n squared. And then what is this thing? Well, we know it's n times n plus 1 over 2. So I got 2 over n squared times the formula we know for this thing. That's n times n plus 1 over 2. And then the last sum, 1 over n cubed. And then what is this sum? Well, we know it's n times n plus 1 times 2n plus 1 over 6. So now from here to here, I've gotten rid of all of the i's. That's good. So now to find the exact answer, let me switch a few things around here. Right, so I know the area, it's the limit as n goes to infinity of my approximation. So that's the limit as n goes to infinity of right? The first thing is 1. The second thing is the 2's cancel, so plus n times n plus 1 over n squared plus, and here I'm going to switch the n cubed and the 6, so 1 over 6 times n plus 1 times 2n plus 1 over n cubed. Okay, so now what is each one of these things? Well, here I'm just going to get a 1. Right here, the degree of the top, this thing is really n squared plus n over n squared. So the degrees of these two polynomials are the same. So the limit is just the ratio of the leading coefficients, so plus 1. And then plus 1 over 6 times. And now here I get the polynomial whose leading term is 2n cubed over n cubed. And so the limit as n goes to infinity is just going to be 2. Right, so here I get 1 plus 1 plus 1/3, and so that's going to be 7/3. So that's the exact answer, right? That's the exact area for the area under this parabola y equals x squared on the interval from 1 to 2.